Thanks, Abhishek, and thanks to both you and Sanjib for this invitation to lecture at the Bangalore Statistical Mechanics School. Uh, I would have been much happier if I could have come to the ICTS campus and interacted with all the students in person. And anyway, it's much easier to give such lectures on blackboards. And yeah, but anyway, so due to COVID, we'll stick to this online mode. And yeah, I'll try to be reasonably detailed. And if you have any questions, then feel free to stop me and I'll be happy to address those. So during my set of 5 lectures, I'll cover some aspects of non-equilibrium and periodically driven quantum systems, mainly theoretical aspects. And this is a very sort of a wide open field in the sense that there are several open questions. So sometimes during the latter part of the course, I'll also sort of highlight the open questions that are there. And then, of course, some of you may be want to try to think about those during your research, right? So, okay, so let's go on. Good. So here is the basic outline of the course. So first, I'll introduce some basic notions of thermalization in isolated quantum many-body systems. And in particular, I'll try to highlight how these notions of thermalization are different from, if you wish, classical Newtonian systems. Okay. After we are done with that, we'll of course then target specific problems to understand different aspects of these things. So the first problem I'll target is, if you wish, the Ising model of these things. So it's an integrable model. It's a very well-known integrable model, the one-dimensional spin-half transverse field Ising model. And maybe some of you already know that this model, you can solve for many things in this model exactly. And it turns out that the same holds true for quantum dynamics, and we can actually try to solve many things here. And you can quickly see many results in front of your own eyes doing your own calculation. So that's why I'll spend some time here. After that, we'll move to some more recent stuff, more recent development in the field. So one of them is called many-body quantum scars. So quantum scars have been something which have been known in quantum few body systems for quite a while now. But for the last, let's say, 4 years or so, there has been a lot of excitement on the many body version of it. And these things have also been seen experimentally. And we'll try to see the consequences of these things. Okay. And then I'll move to the second part of the course, which is periodically driven systems. And I'll, in particular, after, of course, again, highlighting some of the generalities and the basic concepts, after that, I'll devote most of the time to a specific problem, which will actually highlight that for these periodically driven systems, it's actually possible to get phases of matter which are forbidden in equilibrium. So that is very exciting. So one particular case that I'll spend some time on is this so-called time crystal. Again, some of you may have heard about this phrase, but I'll try to demystify what this is. So we'll talk about Fluke time crystals in one dimension, and we'll also sort of introduce the concept of many-body localization, which will play a central role in sort of stabilizing these interesting phases, okay, for periodically driven systems. And then towards the sort of the last lecture or so, if time permits, I'll in fact introduce a concept which is called pre-thermal time crystal, which basically means that in periodically driven systems, depending on certain specific conditions, if you satisfy those, basically there is a very long transient in the system, and in that transient period, one can actually mimic properties of a time crystal without disorder. Okay, so that's very exciting. And ultimately, the system flows to some ultimate steady state. But the crucial bit is that this pre-thermal phase is rather long in time, so you can actually experimentally view it, and that's why it's interesting. Okay, so this is sort of the broad plan of the course, and we'll see how much we can cover during these 5 lectures. Okay, good. So, let's try to define the problem that we are interested in. So imagine that you have an isolated many-body quantum system, and this is the usual drawing we draw to indicate that the system is isolated from the rest of the degrees of freedom in outside the system. Okay, so I'm not considering those degrees of freedom. So there are many degrees of freedom here. There may be interacting spins, interacting fermions, or interacting bosons. But to be very specific, for these lectures, for the sort of the next 5 lectures, we'll just think of interacting quantum spin systems. Okay, so you might want to imagine that there is a lattice. Maybe it's a one-dimensional lattice, maybe a two-dimensional lattice, and there are quantum spins living on the sides of that lattice. Maybe these are spin half degrees of freedom, maybe they're spin 1 degrees of freedom, and maybe there's some interaction like a Heisenberg spin-spin interaction, some magnetic field, and so on. So it's a quantum interacting quantum spin problem. But of course, as I said, you can also think of fermions or bosons. But to be very specific during the lectures, we'll just concentrate on this. Okay. And now, let's say you somehow prepare the system in some initial state. So this is the many-body wave function that I have, psi at time 0. So this represents the many-body wave function. And then I'm doing some purely unitary time evolution. So this indicates my time evolution operator in quantum mechanics. And then, of course, if I propagate the system for time t, I get some final many-body quantum wave function, right? So, of course, there's a horrendously complicated object because there's a quantum many-body wave function, okay? But we'll see that if we ask the right questions, then certain simpler things would emerge from here, okay? So this question of whether quantum systems, many-body quantum systems self-thermalize. This question has a very long theoretical history. I mean, even people like von Neumann, when they were thinking of foundations of quantum mechanics and StatMech, they were worrying about questions like this. Okay, that whether a complicated quantum many-body system can thermalize on its own. Okay, and we'll of course, during the lecture, see what thermalization means here, because we need to be careful. Of course, I'm doing a unitary evolution. So if this is a pure wave function at some time 0, the psi of t remains a pure wave function, right? So it cannot become a mixed wave function, right? So we have to sort of be a bit more careful about what we mean by thermalization and concepts like that. So, so even though this question has a long theoretical history, starting from von Neumann, there has been a tremendous revival, both in theoretical and experimental interest in such questions for the past decade or so. So I'll be very brief about this because I'll primarily talk about some of the theoretical aspects. So there have been a wide variety of synthetic quantum systems or quantum simulators, if you wish, which are experimental platforms where this assumption that the many-body quantum system is very well isolated from the rest of the degrees of freedom or the bath which is living outside the system, this assumption is true for a rather long experimental time scale, okay, in natural units of the experiment, okay, natural time scales of the system. Okay, so some of these systems are like these ultra cold atoms or these trapped ions. Then there are some solid state systems as well, like these NV centers, superconducting qubits, and so on. So there has been a tremendous experimental progress in this for the past 15 years or so. And consequently, of course, these questions have resurfaced and theoretically as well, and people have started thinking about them from a fresh perspective. And we have learned several things during this journey, and there are still many open questions. Okay, so for my purpose, during the lectures, I'll concentrate on 2 specific examples. So during the first 3 lectures or so, I'll just imagine that this unitary dynamics is produced due to a many-body quantum Hamiltonian, which is a static Hamiltonian. There is no evolution in time. So I just prepare my system in some sort of a simple initial state, and hopefully that simple initial state is not in equilibrium or anything, right? It's some out of equilibrium state. And then I just do some unitary quantum dynamics and I look at the properties of that state, okay? So these kinds of things are called quantum quenches. So typically what you do is you prepare the system in the ground state of some sort of a simple Hamiltonian. If it's a magnetic system, then maybe you just put a strong field and you align the spins, and then you switch off the field and turn on some interactions and then see the quantum dynamics. Okay. So, or you can do it in various other ways. Okay. So that's this so-called quantum quench. And then towards the last two lectures or so, I'll switch my focus on this other thing, which is even more interesting because there are many richer possibilities, which is the so-called fluke systems or periodically driven systems. So fluke systems have the property that there is some parameter in your Hamiltonian, maybe the magnetic field, and you're driving that magnetic field periodically in time. Okay, and you keep driving it. So this is a driven system. So of course the system doesn't go into equilibrium, but it goes into a steady state. It goes into a well-defined steady state. And that well-defined steady state may have very interesting properties. So that is those kinds of problems where this is true is this so-called fluke matter, quantum matter. Okay, right. So we'll focus on these two during the lectures. Good. So let's try to properly understand what we mean by thermalization in this setup, right? Because as I said, there's no external bath here. This wave function is pure for all times, right? Because of my initial conditions here, right? So by the way, in principle, I could have started also with the density matrix here and could have also propagated the density matrix. Most of the things that I'm going to change can be easily generalized to that. But for the sake of these lectures, we'll just concentrate on initial conditions where the initial state is a pure state, but a simple pure state. Okay. Right. So what do I mean by proper initial conditions here, right? So for example, think of your magnetic system again. So let's say I concentrate on spin half degrees of freedom in a one-dimensional lattice. So a very simple state that you can imagine is each spin half degree of freedom has its own block sphere, right? So you just put this spin here on the block sphere, this spin here on the block sphere, this spin here, this spin here. So there's a very sort of a simple initial quantum state, right? And I can denote it like that, right? And basically, this is also an unentangled quantum state. We'll come to what is the precise meaning of this term a bit later during the lecture. Okay. Of course, you can create a slightly more complicated state as well, right? So, but let's just stick to that. So now, the second thing which I demand is that this Hamiltonian that I'm talking about, this Hamiltonian, this spin Hamiltonian that I'm talking about, this is local in space. This is the second property that I demand. This is going to be very important for my future discussion. So what do I mean by local in space? So most of the spin problems that you study in textbook, like the Heisenberg model, they have sort of nearest neighbor interactions, right? And then maybe you can put a magnetic field. The magnetic field are on-site terms. Then maybe you can also have a three-spin interaction, right? Some more complicated term. Maybe you can have a four-spin interaction. But whatever it is, there is a finite range of these interactions, right? So in that sense, I would specifically look at Hamiltonians which are local in space. Okay, good. So that's another restriction that I impose. Now the third restriction that I impose is what are the physical quantities that I would calculate to sort of probe this thermalization. Okay, that's very important. So the physical quantities that I would look at are operators, which are again local in space. Okay, so basically the operator can be completely contained in some finite region in space, right? So what do I mean by that? For example, I think of some correlation function. Okay, so maybe I look at a sort of a four-spin correlation function between the spin here and the spin here, right? Now, of course, this operator can be sort of localized, right? Because this is just a four-spin correlation function. Or if you're looking at the total magnetization, let's say you're looking at the Z component of the magnetization, then again, you can write the operator like this. So summation over I, sigma I Z, for example, where sigma I is a Pauli matrix, the Z component is a Pauli matrix, and then you sum over each side, right? So again, it's a sum of local operators. So from my definition, that is also a local operator. So I would consider operators like this. Of course, in quantum mechanics, you can consider more complicated operators, which cannot be fitted into a local region like that. But I'm discounting those operators. And we'll quickly, in this lecture, see why we are discounting those operators as well. But there's also an important point here. Most of the operators which we measure in experiments anyway, even when we study thermalization in sort of classical systems, are again local operators. For example, you measure the correlation functions or things like energy or some fluctuations. They're all sort of local operators. So this is not such a bad restriction, if you wish. Okay. So now the fourth condition that I sort of demand is that, remember I said that I want certain specific initial conditions. So the initial conditions should be sort of simple wave functions, which are sort of unentangled. And so this is very important. Those initial conditions should have sub-extensive uncertainties in conserved quantities. So what do I mean by that? So this is actually important again, even in classical StatMech, because right. So let's see why. What do I mean by that? So suppose I do this dynamics, which is this quantum quench, right? So even though this is a very complicated many-body problem, I know that there are certain conserved quantities here. Okay, so what are those conserved quantities? So for example, one conserved quantity is, let's take your initial state, psi 0. Okay, that's up to you. So let me just calculate this expectation value, psi 0 at psi 0, right? Now, because this evolution is unitary and the unitary operator is just e to the minus iht, right? Because it's a time-independent Hamiltonian, then it's easy to prove that this quantity, even if I calculate it for the many-body wave function after time t, this quantity is a conserved quantity. Okay, so, and this is of course an extensive quantity because this can be expressed as a sum of local energy densities. So this is an extensive quantity. Okay, so the initial condition that I take should have sub-extensive uncertainties in this quantity. So what do I mean? So let's say I take this kind of an initial condition. Now, this kind of an initial condition may not be an eigenstate of your Hamiltonian, of your many-body Hamiltonian. In fact, in general, it would not be an eigenstate of your many-body Hamiltonian. And that's why you would get some non-trivial evolution. Because it's not an energy eigenstate of the many-body Hamiltonian, of course, there is some sort of, if you wish, there is some sort of a fluctuation in the energy, right? But that fluctuation should be sub-extensive. So if I look at the total system with, let's say, capital L spins, the fluctuation should be at most square root of capital L or something like that. But again, if you take reasonable initial conditions like that, this is guaranteed just from the central limit theorem kind of arguments again. Okay, so this is another important thing that I demand. But as I said, this is a very weak condition. This is almost always satisfied for states like this. Okay, good. So now, here is what I mean by thermalization. After I impose all these sort of rather weak restrictions. Okay, so let's say I prepare my system, and let's say I prepare two different initial conditions in an interacting system, and both these initial conditions should have the, let's say, the same energy density, right? Okay, this I can sort of, there are many initial conditions which can have this number being very similar to each other, okay? Right. Then I just propagate the wave function, okay? And I calculate this quantity, where this O is a local operator, okay? Because this O is a local operator, which is, let's say, contained in some subsystem S in my total isolated quantum system. So you can just imagine that this O can be entirely contained in this subsystem. And of course, this S plus S bar is isolated on in totality, okay? Right. So then, even though you're doing unitary quantum evolution, if you do an actual calculation here, or let's say you do an experiment where maybe you do this on the ultra cold atom platform or something like that, then what you see is something very interesting. These initial conditions, even though at time t equal to 0, they have some very different values. Basically, after a reasonable amount of time, they'll just go to some sort of a value, and different initial conditions just go to the same value if they have the same energy density at time t equal to 0. Okay. Now, this is the hallmark of thermalization, right? So thermalization simply means that if I take different initial conditions, which have some conserved quantities which are basically the same, but everything else can be different, right? Then if you propagate the system in time, then basically all the memory of the initial condition is washed out, and the only sort of memory that remains is the memory of those sort of conserved local quantities, right? So that's exactly what happens here. Okay, right. So
question.
Yeah.
And this value in which this two initial conditions saturates, I think I would think that this value should be, so one should be able to compute it from thermal states. Like
no, that's correct.
states.
It is correct. You should be able to compute it from thermal states. I'm going to compute.
And it should match. It should match.
It should match. Of course, it should match. I'm going
Otherwise,
to.
Yeah. Okay.
Yeah. Okay. Any other questions right now?
Yeah, I had one question. So the reason you kept out the, like you put this condition of sub-extensive fluctuations, so that of course means you're leaving out, for example, energy eigenstates, right? So why did you?
No. I'm not leaving out energy eigenstates. That's a very important point.
But
so
this
an energy eigenstate has no fluctuation. So the
okay, so that is also allowed, right? Okay.
However, no. Since you asked that question, however, you should not create sort of a very complicated cat state where, let's say, you're using energies from, let's say, some region with energy E1 and some other region with energy E2, and E1 and E2 are macroscopically separated. That kind of a state would never thermalize under unitary dynamics, right? But that's anyway a rather artificial initial condition, right?
Okay, and that would violate this second condition. Is it sub-extensive uncertainty?
Exactly. You violate that condition, right? So that's why I was careful in defining these conditions.
Okay.
Right. Are there any other questions in the chat? Maybe then.
So Arnab, I have one question.
Yeah.
So in the plot that you had, that it asymptotically reaches a thermal state. So this is for quench, or this is also for the periodic driving where?
Okay. So right now I'm focusing on quench. Okay. And I'll tell you what is the meaning of this O thermal. But during the latter parts of my course, when I'll go to Fluke systems or periodically driven systems, you will see that a similar notion also survives there.
Right. Okay.
Okay. Yeah. Okay. So.
Arnab, there is one question in the chat box.
Oh yeah. So yeah, let me try to read it. Okay. I understand. So the question is. So this is my definition of local operators. Actually, it's a standard definition of local operators. So the question is that why am I calling this operator to be a local operator? Okay. So why am I calling the sum of local operators to be also local operators? So this is a very specific kind of a operator, because I can sort of write this as a sum. It is enough if each term here can be localized in space. That is enough for me. Okay. So suppose I measure something here and I measure something here and I just add those two. That is also a local operator for me. Okay. Suppose I measure something here, here, or here, and I add those three. That is also a local operator for me. So a sum of local operators is also a local operator for me. However, what is a non-local operator? So during these lectures, we'll very quickly encounter a non-local operator, and if there is still some confusion, maybe the person can ask me again. Okay, so this is a very sort of a, not all operators in quantum mechanics satisfy that. This is a very restrictive condition. Okay, so for me, a sum of local operators is also a local operator. Okay, so I'll introduce what is a non-local operator during hopefully this lecture, and if the question or confusion persists, we can come to that point again. Okay, good. Okay.
Hi. This local means, is it always like spatially local on the lattice, or it can be
spatially local? Spatially local. So when I use the term local, I always mean spatially local. Okay. Yeah.
I mean, I can also have something local in momentum space
No,
or
no, that's
something.
correct. You can have it but for these conditions to be true in general, I'm demanding locality in space. So this operator
Okay.
is also local in space, right?
Okay. Thanks. Thanks.
Yeah.
Okay.
Arnab, could you, hi.
Yeah.
Yeah, could you please repeat the last point a bit? Sorry.
Oh, last point to the response to the question.
The set of conditions that you laid down, the last point among them.
Oh,
The
this
extensive.
one, extensive,
Yeah.
this one.
Yeah.
Oh, okay, okay. So I'm saying that, see, suppose you take an arbitrary wave function like this, right? In general, this wave function is not an eigenstate of my many-body Hamiltonian. You agree with that, right?
Yeah. Yeah.
So of course, the energy is not like a delta function, if you wish. There's some fluctuations in the energy, right? I'm just calculating the average here, right? But
Okay.
you can, in principle, calculate fluctuation by looking at h square and then defining some variance and things like that, right?
Yes.
So I'm saying that fluctuation should be sub-extensive,
Oh, okay.
okay, in system size.
Okay. What does sub-extension
Okay,
mean?
so let's just think of normal statistical mechanics system.
Okay.
So again, if I just use central limit theorem here, if I just write down a state like this here, remember the Hamiltonian is also a sum of local quantities, right?
Yes.
So for most things like that, you would see that the range of fluctuations in your energy is sort of square root L if your system size is capital L.
Oh, okay.
And that basically comes from central limit theorem kind of arguments.
Okay. Okay.
So
Thank you.
that's a sub-extensive fluctuation, right?
Okay.
Yeah, because if you divide the fluctuation divided by the mean, then it sort of goes to zero in the thermodynamic limit, right?
Yeah.
So,
Yeah.
yeah. Okay.
Thank you.
So do you mean that if this energy can be written as sum of local energy density?
Of course.
And
Yeah,
this-
yeah. Because you see, I'm
and-
saying that my Hamiltonian is local in space. That's why I can write it
Yeah.
like that. Yeah.
And this sub-extensive concept means that these different local terms, the difference and the fluctuations in these different local terms are of order square root L. If the system, if the number of terms are of order L.
Yeah. I mean, because it's a sum of sort of many terms, right? And let's say there's some notion of a correlation length in your system. Then beyond the correlation length, you could sort of think of the different sort of energy densities at different sites being independent operators, right? And then it's like you're adding lots of independent sort of operators and you get some sort of a central limit theorem kind of a picture, right?
Yeah.
Okay, good. So let me go on. So let me go on. So basically, out of this, we figure out that the system acts as a bath for itself when this thing happens. Okay, so please remember that the system is isolated on its own, right? There's a purely unitary evolution taking place. But if you look at a finite subsystem, so a small subsystem, then the rest of the degrees of the freedom act as a bath for itself. Okay, so maybe put like this does not sound like a terribly surprising statement. Okay, so right. Okay, good.
Hi, Arnab, just one question, sorry. Sorry, so suppose you have this plot, right? So let's say O is still an operator with finite support, but let's say the Hamiltonian itself is a long-range system like a spin chain, okay? But O itself is some chosen operator with finite support.
Right.
Even then, something like this plot is most likely to happen, right?
Yeah. Should happen, but that's a more complicated thing. So for the purpose of these school lectures, I did not go into that.
Okay. Yeah. Thanks.
Yeah, but you're correct. That's for the experts. Okay.
Thanks.
Okay. So good. So yeah, I'm running a bit slow, but that's perfectly all right because I'm very happy to receive questions. Okay. So yeah. Okay. So now let us be slightly more precise. Okay. So first, what do I mean by this thermalization precisely? So first, I take this isolated system, okay, and take the thermodynamic limit of this isolated system. So of course, if there's a spin system in one dimension with capital L sites, I take L to infinity first. Okay. After I take L to infinity, I take any finite subsystem. So remember, I've already taken the thermodynamic limit, and then I take any finite subsystem here. Okay. so I'm considering an arbitrary local operator, then the following is true. So, so you see, I told you that the full quantum evolution is unitary. So if you look at the full density matrix of the system, by definition, the density matrix of the system is this, by definition of the full system. Okay. So yeah, for those people who may not have encountered density matrices in quantum mechanics, maybe you can sort of look up any standard textbook. And I also think there's some sort of a tutorial in Manas's course on density matrices, but we won't use much of the machinery of density matrices. So this is standard quantum mechanics. So the full density matrix of the system is this, and this is always pure. So that means that trace of rho is 1 and trace of rho square is also 1, which is true for pure states. But here comes the important point. Even though the full density matrix is pure, if I look at the properties of a subsystem, one convenient way is to integrate out the degrees of freedom outside this subsystem. Okay, that's one convenient way. Okay, so so if I do that, then I get a reduced density matrix, which is localized in that subsystem denoted by S. So all that I need to do is integrate out the rest of the degrees of freedom. So I have a very simple exercise later on. If some of the students are interested, they can do it. Okay, and then you'll sort of get a feeling for this. So then in quantum mechanics, even if the full density matrix is pure, this reduced density matrix can in principle be mixed, which means that the trace of rho sub s whole square is less than 1. Okay, in principle, that can happen in quantum mechanics. Okay, so now, because my local operator O is confined strictly in S, I can of course calculate it by the standard formula trace of rho sub S P times O, right? I mean, this is what you use in statistical mechanics, right? The only difference here is that this rho sub S comes from this microscopic calculation here. I'm not putting a thermal bath here, right? In normal StatMech, you just say that rho of S is e to the minus beta h divided by the partition function, right? That's your Gibbs ensemble. But here I'm not doing anything like that. So now, after a sufficiently long time, okay, so I have put this in quotes here, but let's just say that if you wait long enough, after a sufficiently long time, this rho S, this reduced density matrix, in fact goes to this form. This is very important. So this rho equilibrium is basically your Gibbs density matrix, e to the minus beta h divided by the partition function, where beta, the inverse temperature, is fixed by the conservation law of energy here, right? So you remember this is a conserved quantity, this guy, right? So if I tell you that this is sort of the energy density in my system, in StatMech, you can sort of write a inverse temperature in a canonical ensemble, which precisely gives you this average energy, right? So that's exactly this equilibrium ensemble. And now this is a mixed density matrix, okay? I'm saying that this thing is going to this limit, okay? So basically I'm saying that how sort of StatMech emerges from this quantum mechanical picture, okay? And you see, I have been careful here. You take the density matrix of the entire system. This is the thermal density matrix because I've put this EQ here. So for concreteness, you can just think of this as the Gibbs density matrix of the full system. And I'm again doing this trace over the rest of the degrees of freedom. Okay. And I'm saying that this reduced density matrix goes to this thing at sufficiently late time. And if that is true, then because this is true, this equation, this is implied. This is implied. Okay. So now there are some crucial points here, which I would like to stress. Okay. So first point is that I'm not doing any time averaging here, unlike in classical systems. So if you wait a sufficiently long amount of time, of course, this is a finite system with capital L degrees of freedom. That's why there's some sort of fluctuations. But if the system is big enough, then this value basically goes to this thermal answer. Okay.
Arnab?
Yeah.
So when you say that's the density matrix of the full system, the equilibrium.
Yeah, yeah.
So you have already assumed a
temperature for the full system.
Correct.
So you're not going to compute the temperature for the subsystem,
Sanjib,
assuming
I can compute the temperature. That's exactly what I said. So the left hand side is a quantum mechanical thing. The right hand side is something different. Okay, the left hand side approaches the right hand side. What is the right hand side? The right hand side is a calculation assuming a mixed density matrix or a Gibbs density matrix, the usual e to the minus beta h, where beta is fixed by this condition of your initial state. This condition. Whatever is your initial energy density, that is a conserved quantity. I just fix my beta by that number. Okay, just by doing a usual statistical mechanics calculation. This is the same thing as we do when we go from a micro-canonical ensemble to a canonical ensemble. Okay, is that clear?
Yeah, but no, only thing I was saying is that when you go from micro-canonical to canonical, so what we do is, okay, we have a full closed system.
Correct.
And then we just basically look at the whatever distribution for a subsystem, right? And that's the canonical.
Correct.
But now here you are saying that even if your full system is like a canonical ensemble, is that what you are saying?
No. I'm not saying that. So you see, I've been reasonably careful here when writing this. Only rho sub s goes to this if this s is a finite thing. So remember, I've taken the thermodynamic limit, and this S is a finite subsystem.
But what is rho EQ?
No. So let me just come to this point, and then I'll come to this. If this S is a large thing, let's say you are taking the subsystem S in such a way that it contains L by 2 number of degrees of freedom, capital L by 2, right? Then this thing would not work. Okay. Then this would not go to this. Okay. In particular, if this subsystem is the entire system, then rho sub s is always a pure system. It can never go to this. Okay. So this rho EQ, so I should have maybe defined it a bit more precisely, or maybe let me see if my Jamboard works. Let me go to that. Right. These are the perils of giving an online lecture. So I think I should stop share here and then share my Jamboard.
Come back later, it's also okay.
Let me just spend 1 minute on this. Okay, this is an important point. So maybe in the question answer session, I'll address this point. Okay, but is my talk visible now?
Yeah, yes.
Okay, yes. Yeah. So just to answer Sanjib's question, rho equilibrium is the Gibbs ensemble for the full system. Okay. So rho equilibrium is just proportional to e to the minus beta h, where h is the Hamiltonian of the full system. Okay. But what I'm saying is that this thing goes to this thing only when this s is much smaller than this s bar. Otherwise, this equation has no sense. Okay, that's the point. Okay, but if there's some
question, so if I understand correctly, basically what you are saying is that, okay, although the full system is like a micro-canonical ensemble, but suppose I compute this rho s for the subsystem, right? So, and then, okay, that should be, now if I just take the Hamiltonian of the full system and just write down the density matrix as e to the power minus beta h. Okay. It's not in that state for the full system, but I just write it down.
Correct.
And just trace over the other
degrees of
freedom, that those two will agree with each other.
Exactly. And by the way, Sanjib, this is not the conventional micro-canonical ensemble, right? Because this is like rho of s is this object, right? So it's a pure state, right? So basically, if you calculate the sort of the entropy of this entire thing, the entropy of the entire thing is 0, right? Because it's in a pure state. Okay. Yeah. So okay. So as I was saying, I was highlighting some crucial differences. So first thing is, no time averaging is required here, unlike in classical systems. In classical systems, there's a notion of a further time averaging, right? And once you do that time averaging at late time, then basically, then you use something called the ergodic hypothesis, and you say that your time average answer is basically equal to your canonical answer or whatever ensemble you're using. Okay, that's the first thing. The second thing is, which is also important, that's why I had to do this thing. The second thing is that S is not weakly coupled to S bar at its boundaries. This is important. See, when we do usual StatMech and canonical ensemble formulations, we sort of assume that this S is weakly coupled to S bar at the boundaries. right? But here I cannot make such a distinction. This is one full interacting system, and I'm just taking a patch in that interacting system, a spatial patch. So I cannot say that this spatial patch interacts with the rest of the things weakly at the boundaries. I mean, I cannot make that distinction. Okay, because I cannot make that distinction, I have to do this. I have to do this partial tracing. Okay. If I could have made this distinction, then you can write this thing more straightforwardly. Okay. And third, as I already answered, referring to Sanjib's question, rho equilibrium is defined by your local conservation law. So in this setup, which I just sort of elaborated on, your energy is sort of the conserved quantity. So the sort of corresponding sort of Lagrange multiplier, if you wish, is beta, the inverse temperature. Maybe you have a system where there is some other conserved quantity. Then you have some other second Lagrange multiplier. Maybe let's say the total number is conserved. Then you have some sort of a mu, a chemical potential, and so on. So this part is sort of the usual thing that you do in statistical mechanics. Okay, the determination of this thing. Okay, but the crucial bit here is modulo the restrictions I was hopefully careful in pointing out. Even though the entire system is always in a pure state, the subsystem or the density matrix of the subsystem actually approaches this. Okay, at reasonably late times. Okay, good. So another natural question is, how do you calculate entropy from this rho sub s? Okay, so this is again reasonably well known in quantum mechanics. So sort of the natural generalization of the, if you wish, the Gibbs entropy or the Shannon entropy, which is the standard formulation of entropy in classical statistical mechanics, is the von Neumann entanglement entropy. Okay, so what do I mean by that? So again, let's imagine that I have a many-body system, and A refers to some subsystem and B refers to sort of the complement of that. Okay, now if I have a pure state, psi AB, such that I cannot write the wave function like that, psi A tensor product with psi B, which basically means that region A is entangled with region B. Okay, so by the way, this initial condition is unentangled by this definition. This initial condition is unentangled by this definition. Okay, but of course, there are many wave functions which don't satisfy this property. Okay, there's a very simple exercise here. So there are many wave functions which don't satisfy this. So if that is true, then if you trace over any subsystem, let's say A or B, then you can easily show that the rest of the, so then you can show that the reduced density matrix is now a mixed density matrix, okay? Because A is entangled to B. And then you can compute the von Neumann entanglement entropy, and that is going to be a finite number. It's not going to be zero. And so suppose you trace over the degrees of freedom in B, okay, then you get some rho sub A, and the entropy of rho sub A, the von Neumann entropy of rho sub A, is simply minus trace of this reduced density matrix times log of this density matrix. And because the initial state is in a pure state, rho sub A is exactly equal to rho sub B. So you see, this is sort of the peculiarity here because you are in a pure state. Imagine a system which has sort of 10,000 spins, but it's in a pure state. And let's say I integrate out 2 spins. And I just say that my subsystem is like that. So let's say there's some finite entanglement in that subsystem, and I calculate this entropy from there. You see, the entropy of that region with 2 spins is exactly the same as the entropy of the rest of the region with 10,000 minus 2 spins, because the entire thing is in a pure state. Because this entropy can only be generated if degrees of freedom in A get entangled with degrees of freedom in B. Okay, so basically that's the sort of intuitive way of understanding why S of rho is equal to S of rho B, because this entropy is only generated due to the entanglement between A and B. Of course, you can prove this more formally, but this is sort of just a hand-waving way of stating this. So this is a simple exercise for people who might not have seen this before, that you can start with a pure state and get a mixed density matrix if you integrate out part of the system. So just take 2 spin half degrees of freedom for simplicity. Just take 2 spin half degrees of freedom. and form a singlet state out of them. So this is your singlet state, right? This is your well-known singlet state. Now this, let's say I ask you to integrate out spin A from here, then you would get a rho sub B. So this is an easy thing to do. You can do it by hand, okay, because there's a very simple wave function. And if you do that, and you then calculate this rho of A, you will actually get log of 2. You will not get 0, simply because A is entangled with B. But if you had chosen the wave function to be up A, down B, and you had forgotten about this part, then this is an unentangled wave function, and then you would have seen that S of rho sub A is equal to S of rho sub B, which is equal to 0. Okay, so this is a very simple exercise that students can do if they have not encountered this thing before. Okay, so yeah. So good. So are there any questions at this point? Otherwise, I'll go on.
Can I ask a question from the previous slide?
Please, previous slide. Yeah.
So here you mentioned that S and S bar need not be weakly coupling.
Correct.
But in classical mechanics, you mentioned that if they are not weakly coupled, then there is a problem. But in classical...
No, I didn't say there's a problem. In the usual way we define canonical ensemble, when we say that there is a system and there is a bath, usually we say that the bath is interacting weakly with the system at the boundaries. Otherwise, it's hard to sort of separate what's a system and what's a bath, right? You see what I'm trying to say?
Yeah. Okay. But yeah. What I was getting at was only way we can go from microcanonical to canonical in classical is to assume that the interaction, the interface energies is sub-extensive. And similar to that, here we are saying...
No, so that extensivity and sub-extensivity is also true here. Okay, it's also true here.
But what I wanted to get at was the operator, since the operator is local, that has taken care of the issue.
No, it hasn't taken care of the issue. So let me see, that is why I was careful to write this. You see, because S is not weakly entangled to S bar. Suppose I have a local operator, I cannot approximate rho equilibrium to be e to the minus beta h of just the system or just the S. You see, that's what you do in the usual canonical formulation where the heat bath is providing you a temperature.
Yes.
Here, that is why I'm doing a more complicated thing. I'm taking the full system, writing the canonical partition function or the canonical density matrix for that, and then tracing out some of the degrees of freedom. Because this is you see what I'm saying, right?
Yes.
Yeah.
Yeah, Arnab, I guess also this result is valid even for if your subsystem is just a single spin, right?
Correct. It's valid. It's valid if the subsystem is a single spin. All I demand, as I said, is that this subsystem should be finite in the thermodynamic limit. So of course it can have 1 spin, 2 spin, 10 spin. As long as it's a finite number, it's okay. Okay. Yeah. By the way. This maybe we'll come to later when we study integrable models. If you take an operator which has a support only on one side, then in some very physical sense, it's a very local operator. On the other hand, if you take an operator which has a support on 10 sides, it's a sort of a slightly more non-local operator. Then if you actually do this computation, you see there's a time scale to approach this thermal answer. That time scale would increase when you go from a very local operator to a slightly more non-local operator to a slightly more non-local operator and so on, which is in some sense intuitive. But when I talk about integrable systems and I just sort of formulate how to do the calculations, of course, I won't go into all the gory details. Then the interested students and participants can do their own calculations and see all that. Okay, yeah. Okay, so if there are no questions on this, let me go on. So,
I don't know. Actually, I had a question.
Yeah.
Regarding the previous slide.
This one?
Slides. No, before this.
This one? Yeah.
Yeah. So even in the case that you're considering, your S is like interacting only at the boundary, right?
Well, in principle, you are correct. But see, if S is very small, no, there's a slight caveat here. If S is very small, then this is not so obvious. You see, suppose S has just 3 spins. and let's say my Hamiltonian has interactions which are range 1, range 2, range 3, range 4, and range 5. Then you cannot very easily make the statement that you're making, right? But if I do this, then everything is still okay. If I do this, you see what I'm trying to say?
Yeah, with very few number of spins.
No, but this equation should hold for an arbitrary S. I need to formulate the problem such that, see, I mean, this is an equation I need to formulate properly, right? So therefore I need these conditions, right? So yeah.
Okay. And secondly, like, what happens to the ergodic property? Like,
no, as I said, you don't need to do any time averaging here. So how do I justify that? Yeah, let's see. Let me sort of give you a cartoon way of understanding that. Okay, I think let me share my full screen, and then I'll be able to see whatever is on my screen. And yeah. Wait, let me just wait. Yeah, now it's okay. So you see, let's consider a classical system now. Okay, so let's say there's some phase space, and here I had started with one particular initial condition, right? So let's say I do the same thing here. Then of course I'll do some very complicated thing, very complicated thing. But it's always one point in phase space, no matter what time you are at, right? So what you need to do is sort of do some notion of time averaging for a reasonable time, which is large compared to your microscopic timescales, to get an ensemble description, right? This is fine. You agree with me on this? Is that okay?
Yes.
Okay. Now let's see what happens for this quantum system. Imagine that you're looking at this quantum system from the same viewpoint. Of course, you cannot, because it's a quantum system. So what that means is there is no way to specify a point in phase space, because there is something called uncertainty principle. So even your initial condition has a bit of a fudge. Sorry, fudge meaning smear, right? Because of the inherent uncertainty in quantum mechanics, right? And that sort of smearing basically gives you a family of initial conditions if you consider things classically, and then there is no need to time average, because once you reach a late time, there is a family of final points. There's a family of final points, and that's it. The ensemble has automatically emerged from here. I don't need to do any average. Is this clear? This is, of course, a very hand-waving argument.
So the point you're trying to make is like there is no like proper notion of this phase space in the
No, that is of course well known in quantum mechanics. You know, you cannot very straightforwardly generalize phase space. Yeah, you can do some path integrals and certain things and introduce some other variables and do it. But what I'm trying to say is, if you think in your classical picture, because in your classical initial condition, there is already a smearing, because there is no way you can precisely satisfy this initial condition, because you see in quantum mechanics, there's an uncertainty. That's why you don't need this additional time averaging here, right? Because, let me use the highlighter. This set of points already go to this set of points here, right? But this won't work if I have a strictly classical description, because if I start with a single point, no matter what I do, it will stay a single point. So you need to therefore do a time average. There is no way out. I hope this is clear. As I said, this is a hand-waving argument, but yeah. So.
But in quantum system also, you can start with a pure.
Sorry, I cannot hear you.
No, in quantum systems also, you start with a pure state, and in the Hilbert space.
That's my assumption. That's my assumption here, because I said that I start like this. Yeah. Of course, in principle, I could have started with a mixed state also and did a unitary propagation. Just to avoid further complications, I'm not doing that. But all the things that I'm saying can be generalized there as well. But please go on. Yeah.
Could you please explain this mirroring out at the initial state in the context of quantum?
No, sorry, I did not. Can you speak a bit louder? Your microphone is very.
Can you hear me now?
Yeah.
Is it okay? No, I'm saying, could you please explain this mirroring out as initial state in the context of
No, this was just in response. Sorry, maybe it was a useless digression, but this was just in response to the previous question about why I don't need time averaging in these quantum thermalization things. Okay, so you see, of course, if you do an exact calculation, you will see that at late time, the answer really goes to O thermal. You don't need to time average. At any late time, this is true. But of course, I'm trying to give you hand waving argument. So what is the hand waving argument? The hand waving argument is, imagine that you have a classical system. Why do I need a time averaging here? So classical system. So in this classical system, if I did the analog of this, what is the analog of this? I start with a precise point in phase space, right? I don't consider some kind of a sort of a probability density here. I start from a precise point in phase space. Then, no matter how complicated your equation of motion is, it'll still be a point in phase space at any late time, no matter how long you go. Of course, this is a chaotic equation and all that, but this is still true that it's still a point at late time. So, to see an ensemble description, what you need to do is consider a sort of a sequence of points. Okay, for this trajectory. And then if you look at all of these together, then you can sort of use a canonical description or something like that for classical systems. Okay, so yeah, that's the standard thing in classical systems. Now here, how does this picture fail? Why do I not need any time averaging? That's what I was trying to say in some sort of a hand-waving physical manner. So the reason this picture fails is the following. The reason this picture fails is I fail in step 1. So in my phase space, if I try to denote this thing, okay, then I cannot denote it by a point, because in quantum mechanics, there's something like an uncertainty principle. So basically, if you want to think sort of classically, this point has sort of smeared out because your h power is not equal to 0. Okay. And then if you again want to think sort of semi-classically, each of these points is doing some complicated motion, right? Something like this. But you see, because I've started with this thing at time t equal to 0, at some late time, I'll just look at the collection of all these things at time t, right? Some time t. And that's why I don't need this further averaging. That's why I don't need this further averaging. That is what I was trying to,
If you bring a semi-classical type of description in this.
Well, I don't really want to bring it here because that's very complicated. I want to avoid that path, but yeah. But this is just a hand-waving description of the true thing.
Okay. I have one question from the slide.
Okay, so maybe so I think because I'm sharing my desktop now, I can just do this. Is my slide visible? And now I guess I go to full screen.
You have to increase the size.
Sorry?
You have to increase the size.
Oh, yeah. Sorry, just 1 second. Please give me some time. Sorry. Here. Go on.
So this rho st goes to trace s bar rho equilibrium. This rho equilibrium for the full system. This statement is observed in many simulations and calculations arguments. Is this proved?
So in many numerical computations, it has been proved. So by the way, I'll come to my, I'll soon introduce something called the eigenstate thermalization hypothesis. And if you assume that is true, then this statement is true. But there is no strict proof of the eigenstate thermalization hypothesis. Nobody knows how to prove it for a generic quantum system. Okay. So basically, you can just think of it as an assumption. And this happens to be true in most of the numerical calculations. And it happens to be true in those experimental platforms that I was talking about. And in fact, there are also very interesting examples where this is not true. And in fact, they'll be the prime players in the future lectures of my course. But yeah, so there are lots of subtleties here. There's no analytic proof for this statement. Yeah.
Thank you.
But you see, I mean, this is a sort of if you think sort of loosely, imagine that you have a very complicated quantum system with lots of degrees of freedom. It's intuitively clear that something like this should happen. If you, I mean, just focus on a patch of the system and the rest of the degrees of freedom are sort of, providing a bath to it. I mean, sort of intuitively it's clear.
Yeah, typically for many initial states it will happen, but you can always think of a state in which this may not happen.
By the way, I was careful in defining what initial states were. So here, yeah. So
I'm saying typically many initial states this will happen, but you can pathologically probably find
of course. No, that is true. That is of course true. Yeah, that is of course true. Yeah, correct. Yeah.
So Arnab, in simulation, do you compute the density matrix or some other observable? Which
no, you can actually compute the density matrix, Sanjib. So in simulations, so for the transverse field Ising model, because of the integrability of the model, you can actually do those calculations. Oh, here, let me show this. This is an actual calculation of computation of density matrices for a patch, and then just showing that that density matrix actually equals the stacknet density matrix. So these two are different calculations. These dots are numerical points, okay, and these lines are some canonical ensemble calculation of the full system, okay. And
so
this model
matrix is in some basis, is it? No, because
you always choose some convenient basis and do the trace, as is usual in quantum mechanics. Yeah. So I hope to, by the end of tomorrow's lecture, be able to give everybody the machinery to even compute curves like this for integrable systems. And these are on some humongously large system size. Let's say capital L is some 10,000 or something like that, okay, because of the integrability here. Of course, you can also calculate it for generic quantum systems where you have to use exact diagonalization, okay, and we'll come to some of those aspects, okay. Yeah.
Okay. So yeah, just a small query actually. So you mentioned that this transverse field Ising model is integrable. So I mean, can we? Is it always correct to say that like even integrable systems can thermalize, or is there any?
We'll come to these, right? So I should not jump the gun, right? So we'll come to that. There's a sequence I want to. Yeah.
Okay.
Yeah.
Yes, please.
Yeah. Okay. So good, but this calculation.
Can you hear me?
Yes.
Yeah, I also have a simple question regarding this tracing of the subsystem.
Yes.
If I take a initial condition, which is a energy eigenstate.
Correct.
Then I do a unitary evolution for the full system.
Correct.
Then shouldn't it be again the
wonderful
energy?
Very good that you asked this question. Good. I was anticipating this question. You see this thick dotted line here?
Yeah.
So this thick dotted line is when the psi of p is an energy eigenstate, basically at the same energy density as these two guys are, right? But because it's an energy eigenstate, of course, there is no further evolution. It's just acquiring a phase factor. But the phase factor cancels here and here. That's it, right? So this line is completely flat. And that's basically the one way of posing eigenstate thermalization hypothesis, which basically says that if you look at high energy eigenstates of an interacting quantum system, locally those quantum energy eigenstates look thermal. That's the answer to your question. Okay. And of course, if you do an actual calculation, you will see this dotted line. Okay.
Yeah, but I understood this, but in the calculation, but why would the full density matrix go to an equilibrium density matrix of the full system?
Oh, but you'll have to wait to yeah. I mean, that's the thing about I mean, that's some rather remarkable property of high energy eigenstates, right? But yeah, let's wait for a bit. Yeah.
Okay. So thank you very much.
Okay. So yeah. So good. So basically, as I told you, there is no heat bath here, right? I'm doing a purely unitary evolution. So how is the system sort of reaching a sort of a canonical ensemble, if you wish, when you look at local properties? That's the question. Okay. The way it's doing it is the following. So as I told you, I only start with sort of states. Again, imagine each of these dots is a spin half degree of freedom. I only start with an initial state typically which has very low entanglement. Actually, you can start with an initial state which has zero entanglement. But here, basically, these lines just mean that this degree of freedom is entangled to this guy. this degree of freedom is entangled with that guy. That's all it means. Okay. So this is very low entanglement. Okay. So then typically when I do this unitary quantum evolution, then something very interesting happens. Of course, it's a purely unitary quantum evolution. So the information of the pure quantum state cannot be lost. It just spreads in your entire system. So now I'm using some loose words. Of course, you can calculationally show all this. So this information about the initial state just spreads. Okay. And the way it spreads is, suppose this degree of freedom, this guy, interacts with this degree of freedom. And then these guys become entangled. Okay. Then at some later time, maybe this degree of freedom interacts with this degree of freedom and they become entangled to each other. But then what also happens is this degree of freedom becomes entangled to this guy. Okay, this is usually how quantum entanglement progresses. So after a reasonably short time, what you see here is a very complicated entanglement structure, where again, these lines sort of tell you that these quantum entanglements spread in a very complicated way. And so what happens is that all the information that is stored in your initial state sort of spreads in highly non-local correlations or highly non-local correlation functions in space, which are basically inaccessible to local probes or local operators. Okay. And the only things that you're sort of sensitive to is these conservation laws. And then it's not so inconceivable to think that you again approach a ensemble description if you look at local properties. So the crucial point here is that the unitary evolution spreads the quantum entanglement in some very complicated way from the initial state. And then these things, to access all this information, you need to measure some highly non-local operators. Okay, you cannot, there's no way you can access this information just by looking at local probes. Okay, and that's why if you just measure local quantities, you are not actually realizing the fact that it's a pure system. Okay, so that's the sort of a loose way of stating this. But of course, when we do calculations, we'll be more precise. Okay, good. So, so when we are describing quenches, so what do we typically do? We prepare our initial state in some initial condition, and then we change some coupling of the Hamiltonian suddenly. And then that initial condition no longer remains an eigenstate of the final Hamiltonian. Let's say there's a coupling psi1 at which I prepare some ground state. This is energy. Okay. By the way, this color coding is supposed to indicate the usual fact that near the ground state or near the highest excited state. So because I'm considering spin problems with bounded Hilbert spaces, basically the very high energy excitations can just be thought of as the ground state of minus h. Suppose this is the ground state of h, this guy is just the ground state of minus h. That's it, right? So basically here and here, the physics is dominated by the ground state or excited states with a small number of quasi-particles. And that's the usual thing that we study in courses of statistical mechanics and condensed matter physics, right? Right? And that's also how we study phase transition. Suppose there's a coupling in the theory which is lambda 1, and you change the coupling a bit to lambda 2. As long as you're not crossing a phase transition, the nature of the ground states and the low-lying excitations remain basically the same, right? And however, if you sort of cross a phase transition, then there's a drastic difference, right? These are the usual things that we study here. But here, because I'm doing a quench, so let's say I prepare my system in the ground state of this Hamiltonian with coupling lambda 1, let's say. And from quantum statistical mechanics, it's actually well known that ground states of many body Hamiltonians under very reasonable conditions have something called as area law entanglement of entropy. So we'll come to that. So they have low entanglement. That's the crucial bit. So they are like states like this. They are states like this. Okay, they are not states like this. So then, if you quench this ground state, okay, if you quench this ground state to some other Hamiltonian with some coupling lambda 2, and then do a time evolution keeping this coupling fixed, then what is the usual thing that you would do in quantum mechanics? You would just express this initial condition in terms of the energy eigenstates of this Hamiltonian, right? When you do that, and when you see when these mod of CIs are substantially non-zero, that's what this sort of picture is supposed to indicate. You see that these mod of CIs are substantially non-zero at some extensive energy. That's point number one. And the point number two is that their spread is sub-extensive. Okay, their spread is sub-extensive in system size. Typically, it's square root volume in system size. Okay. Okay, so if I just express this thing in this basis and sort of just draw a plot where I sort of mark the energy where mod of Ci square is substantially greater than 0, right? Of course, mod of Ci square is always lower than 1, but yeah. So now, there's a simple way of propagating this thing in time in this basis. Of course, there's a many body problem. So this right-hand side is immensely complicated because suppose you have a system with capital N spins and they spin half degrees of freedom, then there are 2 raised to the power n states here, right? So that's a very complicated thing. But let's just go on with this formal thing. Then the right-hand side, just by inserting this O here, and now the action of the Hamiltonian is very simple on psi of p. The unitary evolution just gives you a e to the minus I e I t when you look here, right? And then you can convince yourself that you get something like this. Now this answer has two parts. This answer has 2 parts. One part is one part is this time-dependent part. You see this guy in red, and this is basically this guy, this number, this time dependent. There's no time, yeah, there's no time dependence here. This is the other thing, which contains time. And basically, step 1 is that these things decay in time. Okay, if you wait sufficiently long enough for a many-body system, roughly speaking, it happens because if you look at the energy levels of a many-body system, right, it has all kinds of energies, right? Typically, they are highly irrational numbers. So these energy differences are sort of some very complicated set of incommensurate frequencies. So, but this is just part of the story. There's something even more complicated and beautiful, but I won't go into that for the set of these 5 lectures, okay? But let's focus on these things. So basically, I was talking about this eigenstate thermalization hypothesis. So the only way this thing can go to a thermal answer and the answer can become independent of my initial state is the following. So of course, if you take some slightly different initial state here with basically the same energy density, you would get some slightly different CIs here, but nonetheless, they'll be centered around the same energy, total extensive energy, right? So basically, what may happen to make this red guy independent of the initial state is the following. In a small energy window, which is indicated here, if you choose any eigenstate such that if this local correlation function is insensitive to that eigenstate in that small energy window, then I can take this thing out of the sum, right? I can take this thing out. That's an assumption I'm making, by the way. I'm making this assumption. So if I make this assumption, I take this thing out, then I'm just left with summation of I mod Ci square. But this is 1 by definition. Okay, so if you let me have this assumption, which I just now made, which is basically saying that the energy eigenstates appear thermal for local operators, then I have basically proven to you how this thing happens. Okay, I've proven to you how this thing happens. Of course, I haven't told you how this thing decays to 0, this part, how this part decays to 0. There's a lot of rich physics here, and there is a version of eigenstate thermalization hypothesis even for these off-diagonal matrix elements here. But that's more complicated, and we won't go into that in this lecture, okay? But let's just focus on this thing. So basically, whatever I was saying would be true if I make the one assumption that energy eigenstates at some particular energy density appear thermal for local operators where the temperature of whatever I'm calling thermal is set by the energy density of that particular eigenstate. That is one way of stating the eigenstate thermalization hypothesis in a generic many-body quantum system. Okay, so that is basically this red part. So let me pause here if somebody has any questions at this point.
So what do you mean by energy density of that particular eigenstate?
Energy density just means that you take that eigenstate, right? It's a thermodynamically large system. You take the energy of that eigenstate, the energy would typically scale extensively with the system size. Energy density is just that you normalize the Hamiltonian with the number of sides. So it becomes an intensive object. That's it. Yeah.
So Arnab, again, there was a question in the chat box asking to explain extensivity. So I guess extensivity is just like if you take h square expectation minus h expectation square, that goes as n, right?
No, that is basically a statement about the fluctuations. Okay. So
sub-extensivity, sorry.
Sub-extensivity. Yeah, you are correct. Absolutely. That's right. Yeah. It goes as n or even smaller than that. For an eigenstate, it's actually 0, right? But for typical states, it goes as n. Yeah. That's the statement of sub-extensivity. Exactly. Yeah. Yeah.
So if we don't have the sub-extensive property, then in this proof, or in this statement, are you trying to say that this expectation value of O operator sandwich between these eigenstates, you cannot take that out of the summation?
No, so let me explain what is going to happen. It's sort of simple to explain now that I've drawn this picture. Okay. So imagine that you're preparing your system in a very funny sort of a cat state or something. Imagine, okay, such that when you write the decomposition in this basis, right? Then let's say the CIs are concentrated both here. I hope you can see my cursor, and here and here. Okay. Right. So they are concentrated both here and here. And of course, these energies are extensively different from each other. Then what is going to happen is, basically, if you think of what a thermal ensemble is, you can define a temperature T1 for this guy. You can define a temperature for T2 for this guy. And clearly, the system cannot go to a unique temperature. I mean, it'll just go back and forth between some T1, T2, or some intermediate thing in between as you keep doing this dynamics. That is simply because you're starting from an initial state where your initial condition has so much fluctuations that you cannot associate a well-defined temperature. That's all.
Okay, great. Thank you.
Yeah. Any other questions?
Sorry, there was some other.
Yeah, Abhishek, go on. I'll ask later.
Yeah, so this, I mean, the density of states, I thought it's like if you count the total number of states till E, then del, if I call that omega E, then del omega by del E, right? Is that?
Or an even easier thing. I mean, you just define a small delta E here, and you just literally count the number of
states, right?
That's it. Yeah.
Right.
So typically, if you're considering high energy states like here, right, then that number of states in a tiny energy window is basically exponentially large in system size, right? But of course, we know that is not true if you go near the eigenstate, near the ground state here or here. Of course, that is not true. Yeah, that's then typically polynomial. Yeah.
That the density of states can be used to define the temperature at that energy, right?
Yeah, you can do that as well. Yes, you can do that as well. Because you can do that as well. Because normally one way of doing canonical partition functions and all is you can actually look at the density of states as well, and if you wish to find an entropy and a temperature, or do an inverse Laplace transform, yeah, you can do all that. Yeah.
Hi.
Hello. Yes.
Yeah. Am I audible?
Yes.
Okay, so my question was that, okay, this way of defining this ETH, this Srednicki and Sart's type, that for the operator elements you have a certain form for the diagonal or off diagonal elements. So
off diagonal, I'm not talking about this because that's more complicated. Let's focus on the diagonal.
Right. So could we call this like macroscopic way of looking at ETH or something?
I don't know. What is the microscopic way of looking at ETH?
So that would be the other way. If you go back just to the slides when you had the row equilibrium and all.
Okay. So this is the statement of thermalization. Okay.
So,
I'm saying that one conceivable way that this happens is through this. That's what I'm saying. Yeah. And in fact, this statement appears to be true in many systems based on numerical calculations and other observations. But again, there is no analytic proof for this.
Actually, I was saying in the sense, they both don't have analytic proofs, right? This statement.
Correct. They don't have analytic proofs. Correct.
So I was saying in the sense that when we are talking about subsystems, then it's like a microscopic way of talking about it, which was the previous
I don't know.
one.
I mean, I'm not comfortable with that phrasing, but okay, I don't want to debate that. I mean,
Right. So I also wanted to then know that how these are related. For instance,
I mean,
how we could go from
as I just now said, one way that this thing happens for a variety of initial conditions, is if I assume this. That's what I said. Okay. So if I assume ETH, then thermalization is guaranteed for a large class of initial states. Okay. Yeah.
Thanks.
Okay, by the way, I did not sort of stress on one statement. I don't know, how am I doing with time?
You have like 6 minutes, I think.
Oh, okay. I see. Yeah, maybe I'll go 5 minutes extra or something like that, if that's okay.
Yeah, that's okay.
Yeah, sorry. Yeah, okay. So you see, one thing that I did not stress again is that these high energy states. So remember, I said that unless you are crossing a phase transition in like usual condensed matter systems, the ground states don't change much in character, right? However, if you look at any highly excited state here, and even if you change this coupling by a small amount, and you sort of express this highly excited state in this new basis, basically the highly excited state here looks like a completely random state in this new basis. Okay. So what that means is that highly excited states are extremely susceptible to even tiny perturbations. And that is basically because in response to Abhishek's question, as I said, the sort of density of states is very high here. So even a small perturbation is enough to mix lots of states here, right? When you go from here to here. Okay. Right. So, but that's not obviously true here, because as we know from usual perturbation theory and definitions of when systems are in the same phase and not in the same phase. Good. So one thing which I wanted to stress, I think there was also a question previously. I said this operator O needs to be a local operator. Remember, I said this operator O needs to be a local operator. Now you may ask, can I write a proper operator in quantum mechanics which does not thermalize in this setup? Of course, the answer is yes. In fact, I can write lots of such operators. Let's see how to do that. Let me just show you a specific example. So you can see this operator. So this is just the out. So this EM is basically the eigenstate at one particular high energy eigenstate, let's say here. And En is some other slightly different energy eigenstate, right? So this operator is a perfectly legitimate quantum operator, right? This guy, which I have formed here. This is an outer product, right? So this operator can never thermalize by that unitary dynamics. Why? This is very simple. So this I leave as an exercise for you. Take this operator here, and insert this in this formula. Insert this in this formula. Then you would see that you would get only basically two terms here. Okay, you will only get sort of two terms here, and it's impossible that there'll be a dephasing of lots of incommensurate phases here. And what you should be able to show is that at any time t, this guy looks like cos Em minus En times t. Now, of course, this function does not have a large time limit. obviously, because this is an oscillatory function with modulus 1. This, this function does not have a large time limit. So there is no way that this thing would happen for this function. There's no way that this thing would happen for this function. So why did I say that this is a non-local operator? So one simple way of looking at it is the following. So let me just write out what these EMs and ENs are. So let's say I choose a particular basis to write out this operator. So one convenient basis is the usual basis of SZ spins that we take, right? So suppose you have a capital N spins in your, sorry, not capital N, because I have used N here, sorry. Let's say you have capital L spins. Okay, then of course, you know that one complete basis is the basis of all SZs, right? The tensor product of all SZs, and that gives you 2 raised to the power L states, right? And that's this capital N here, right? And that's one complete basis in quantum mechanics. So let's say I write out this wave function, high energy wave function, expanded in that basis. So this alpha 1, alpha 2, whatever are the coefficients that I get when I expand this thing in that basis. Okay. Similarly, this is sort of the bra, and I get this. Then I take the outer product of this guy. Of course, there's a Hermitian conjugate here as well. I'm not writing that out, but I take the outer product of that guy. Then I get a capital N cross capital N matrix, right? And again, capital N is 2 raised to the power L. Okay. So I get some big matrix with these coefficients. Now, usually, if you take a local operator, usually this matrix is a very sparse matrix. Okay, if you take a local operator. Why? Because imagine that you have a state with all up spins. Okay, and let's say you go to spin 5 and you're trying to do something by a local operator. That state is just maybe that operator just flips spin 5 or maybe spin 6 and maybe spin 7, right? So basically, that local operator connects each sort of state here to only a very small number of states, okay, in a usual local operator. But here, and that means in matrix language that this matrix is highly sparse. Most of the entries here are 0. But here, you see that this matrix is highly non-sparse. Why? Because as I said, if you expand the high energy state in any basis, basically you will just get lots of random numbers, pseudo-random numbers, of course. These are not strictly random numbers, pseudo-random numbers, okay? So all these guys are basically typically non-zero, and this is a highly non-sparse matrix. And if you want to represent such an operator in real space, so let's say you are very brave and you want to represent such an operator somehow by some real space formulation, then you will see that you have to write a highly non-local description in real space to get such a matrix. Okay, and then it's clear that those, at least there's a class of non-local operators which does not terminate. That's why this locality is so important here. Okay, so so as I said, so I don't know if there's any question here.
Yeah, they're like even if m equal to n, then also it's not sparse, right?
What matrix. Is sorry? What is m here? Small n.
M and small m and small n.
No. So see. M is just a running index. M is just the index of this guy, and n is the index of this guy. And for me, this m and n are 2 high energy states. Okay, as long as this thing is not exactly 0, this thing is not exactly 0. There is no way that this thing can go to 0, right?
No,
yeah.
I mean, I thought like for if you see the definition of the operator, like
this guy, here.
Yeah, they're like no in the first line.
This one.
Like for n equal to m, this will be local operator, right?
Oh no. I mean, then it's just like a projection operator again. Projection operators for arbitrary eigenstates cannot be written locally. No, you can try to do that. It's a fun exercise. You will soon convince yourself you cannot do it. See, you want to write a projection operator to make your system go into a particular eigenstate. You cannot write a local projection operator. No.
Okay.
Yeah, I mean, this is a property of quantum mechanics. Yeah. Okay.
Hi, actually, related to the last slide, you sort of pulled out this expectation value of O outside the summation, right?
Yeah.
So for the local operators and this local Hamiltonians, is it sort of rigorously provable
No,
that like
as I
it's a
said in the
smooth
answer
function?
to some question, it's not rigorously proved. That's why it's called eigenstate thermalization hypothesis. Okay. The only thing where it's sort of semi-rigorously proved in is in some semi-classical limits. Okay. But for most quantum systems which are away from semi-classical limits, in fact, most quantum systems are away from semi-classical limit. And for most quantum systems which have reasonable local Hamiltonians, there is no proof for this statement. Yeah, no analytic proof for this statement. Yeah.
And what is the typical hand wavy justification? I sorry missed.
Sorry, as I said, I think I said that. So the justification is, you see, if you take any sort of reasonable initial state here and you expand it in this basis here, so these mod of CIs can only be large in a small sort of a patch in energy. And typically that patch has a sort of a square root of system size fluctuation, okay, in response to several questions during the lecture. Okay, this is the sub-extensivity property. So then basically that means that this extensive value of energy is only slightly different here as well as here, right? Because the total energy is extensive. Now what I'm saying is, let me make the assumption, which is the eigenstate thermalization assumption, hypothesis assumption, that if I look at any eigenstate at some energy density and some other eigenstate at some same energy density, okay, then if this local quantity, if this matrix element, this local matrix element appears to be thermal or is just a function of that energy density, then I can pull it out here, right? Then I can pull it out, because this thing is basically, in terms of energy density, CI mod of CI square is a delta function, right? Because that's what sub-extensive things mean. Because if you divide it by the extensive thing, then it's scaling as 1 by square root of volume. So in the thermodynamic limit, it's a delta function. So I just pull this thing out, and then by definition, this guy is 1 by definition. Yeah. So then, and that's how this thing happens. This is one way in which this thing happens, right? So,
okay. Yeah. Thanks.
Yeah. So I see that I'm running out of time. Maybe I'll take 2 more minutes and then stop for questions. So as I already said, unlike ground states of local Hamiltonian, which satisfy something called as area loss scaling of entanglement entropy, we'll come to more details of these things later. The highly excited eigenstates follow something called the volume law. Okay, one simple way of seeing that is, you see, for a finite subsystem, I said that the von Neumann entanglement entropy should scale as should approach the thermal entropy. But the thermal entropy increases as you increase your subsystem dimension. Okay, so this volume law simply states that if you keep increasing the number of degrees of freedom in your finite subsystem, okay, then the entanglement entropy increases in proportion to it. Okay, yeah. So there is a huge distinction between entanglement properties of ground states and excited eigenstates of many-body Hamiltonian. Now, there is another fun fact here, which I won't be able to prove in these lectures, but there's a fun fact. Typically, any eigenstate, many-body eigenstate, which follows an area law of entanglement entropy, typically it can be written as a ground state of a local in space Hamiltonian. But any state which follows a volume law entanglement entropy cannot be written as the ground state of any local in space Hamiltonian. Okay. So, so for example, this state, sorry, I need to drink some water. For example, this state, there's also a pure wave function. So you can ask a question, you can ask a sort of an inverse question. Can I write this state as a ground state of some local in space Hamiltonian? The answer turns out to be typically no. Okay, so there is a clear distinction between such states and such states. Okay, right. And as I also said, ETH implies thermalizations of subsystems. Note, I'm being careful in saying thermalization of subsystems. I'm not saying thermalization of the full system, because the full system because I'm doing a unitary time evolution, and for me, I'm taking an initial condition which is a pure state by choice. The full system is also pure state. So there is no way the full system can thermalize, right? The total entanglement entropy of the full system is precisely zero. It cannot thermalize. So, but the subsystems can thermalize, and one way they do thermalize is this eigenstate thermalization hypothesis. Now, during the rest of these lectures, of course, whenever the opportunity arises, I'll expand on the statement. But another very interesting thing which we'll sort of understand during the course of the other lectures in this lecture series is, it seems very plausible that a many-body interacting quantum system sort of acts as a heat bath for its subsystems. This seems a very physically plausible system. Okay, so the system self-thermalizes. That's one way of posing it, stating it. The question is, are there genuine interacting quantum systems which fail to self-thermalize? Okay, so are there interacting quantum systems, many-body quantum systems, which fail to thermalize or which fail to satisfy ETH, and then the rest of the system does not act as heat bath for the subsystems, and then you can actually have some richer structure here in the subsystems, which is much richer than just a thermal density matrix. That's the motivation. I hope you can see the motivation, right? And in fact, it turns out that there are several very interesting systems like that. So we'll talk about these things in detail. I'll just briefly summarize these things in 2-3 minutes, and then I'll stop for questions. So basically, one of the central questions is violations of eigenstate thermalization hypothesis in interacting systems. Is it at all possible? Now, you see, this question also has a long history, exactly like thermalization of systems undergoing unitary evolution has a long history. Von Neumann and other people were thinking about them from the 1930s, about these questions. So similarly, this question, violation of ETH in interacting systems, this again has a long history. It's just that the field has been rejuvenated in the last decade or so, because we have now achieved different point of views of looking at it. Okay. So in this famous paper by Anderson, where basically, if you read part of the introduction here, he in fact states that he basically is thinking about real physical systems with an infinite number of degrees of freedom, having no obvious oversimplification, in which the approach to equilibrium is simply impossible. Okay, so in particular, it re-emphasizes the caution with which we must treat ideas such as the thermodynamic system of sort of ignore spin interactions, because he's talking about some particular system, when there is no obvious contact with a real external heat bath, because he's thinking about self-thermalizing system. So even people like Anderson were worrying about these questions in the 50s and 60s. Of course, this part of the paper was forgotten because Anderson, in this tour de force paper, later showed that if you have non-interacting systems where he could do calculations, then he showed that you actually get something called Anderson localization, which is a non-interacting version of a system which never thermalizes. Okay, but in fact, now we know that in fact there are interacting versions of basically what Anderson was saying, which are called many-body localized system or many-body localization. And then there are some other systems. So tomorrow I'll start with these integrable systems, which are very nice also from a pedagogical point of view, because in integrable systems also I'll show that ETH is not true. And the nice thing about the particular integrable model that I'll talk is that using some simple mathematical tricks, you will be very easily able to do many calculations on your own in your Mathematica or in your C code. So I'll hopefully reach some point of, I'll of course not give you all the details tomorrow for integrable systems. It's a vast topic, but hopefully by the end of tomorrow, you will reach a point so that you will be able to do some calculations of some of the slides that I show you. And then it's very satisfactory because you see all these things emerging, which I'm just talking about in words. So I think tonight in the tutorial, I think Junaid will briefly introduce something called the Jordan-Wigner transformation in one-dimensional transverse field Ising model. So that's something which I'll require tomorrow. So please pay attention to that. So maybe I'll just keep this slide and not talk anymore. And maybe this is a good point for me to stop and for this lecture and take any questions that you may have. Thank you.
Thanks, Arnab. So there in the chat box, there is, I think, a couple of questions.
Oh, okay. So let me try to go to the chat box. Chats, yeah. So Shoptoshi had a question. Could you repeat the sparseness of the operator related to ETH? I think now I can exit the full screen mode because now I need to write. So how should I do it? How do I? Yeah. So let's see. Abhishek, can you confirm if my Jamboard is visible?
Yeah.
Okay. Sorry, I would have to give you some pain and ask you to repeat some of the other questions because now I cannot see the chat box.
Yeah. There's only one other question.
Yeah, but Shoptoshi's question was about this sparse matrix, right? So you see, suppose you have a local operator. Suppose the local operator is just a spin flip operator.
We can't see what you.
Oh, sorry. I'm in page 2. Sorry. Yeah. Can you see now?
Yeah.
So suppose I choose a particular site. This is a local operator, right? And there are many spins in my system. Let's say this is the particular site, right? This, of course, all of you would agree this is a local operator. By the way, by my definition, this guy is also a local operator. So what does this thing do in the standard basis of SIZ? What does this thing do? All that it does is if it sees an upspin, it makes it a downspin. If it sees a downspin, it makes it an upspin, right? So then you see, suppose I have a basis state like this. This is the 0. This basis state is only connected to this guy in your giant matrix. It's only connected to this guy. It's not connected to anything else through the action of this operator, right? Similarly, if you have a state where you have, let's say, some other thing, let's say this is your O, this guy is only connected to this guy, is not connected to anything else. So obviously, if you write the matrix representation, in this basis, and of course, that matrix is a 2 to the L cross 2 to the L matrix, it's a very sparse matrix. Let's say I arrange my numbering of states on my computer in such a way that this guy is just a neighbor of this guy on my computer in the way I sort of handle the basis. Then in some sense, this is just a tridiagonal matrix, right? This guy. Whereas the matrix I was alluding to is a highly non-sparse matrix, right? So that's the difference between the matrix representation of local operators versus non-local operators, right? Okay, yeah. I hope that is clear.
Okay, so the other question is it necessary the operator O to have support only in the subsystem for ETH statement?
Yeah.
Can we have operator O, which is sum of local operators, but have full support in the full system?
Oh, yeah. The answer to that is yes, because this is an example of such an operator. Yes, the answer to that is yes. Okay. So this has support over the entire thing, but it's just a sum over all the different local operators.
Arnab, I have a very, a trivial question. If the system is gapped or if it is not gapped, gapless, does that make any difference?
Not to these things, because you see, as I said, we are typically focusing on high energy eigenstates, right?
Oh, okay.
So in high energy eigenstates, anyway, because of the property of density of states, the gap is exponentially small in the system size for any generic system. Okay, so.
Oh, okay.
Okay, so I think maybe today we should. It's a good time to stop.